Today we'll discuss about an easy but very important theorem, the fundamental theorem of arithmetic. To understand this, let us take some large number, say 32760, and factorize it as shown using factor of 3. 32760 is written as 2 into 16380. 16380 is factorized as 2 into 8190. 8190 is factorized as 2 into 4095. 4095 is factorized as 3 into 1365. 1365 is factorized as 3 into 455. 455 is factorized as 5 into 91. 91 is factorized as 7 into 13. So we have factorized 32760 as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13 as product of prime. That is 32760 is equal to 2 cube into 3 square into 5 into 7 into 13 as product of powers of primes. Let us try another number, say 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written as 3 square into 3803 into 3607. Of course, we have to check that 3803 and 3607 are primes. If we try it out for several other numbers, this leads us to conjecture that every composite number can be written as product of power of primes. In fact, this statement is true and is called the fundamental theorem of arithmetic because of its basic crucial importance to the study of integer. Let us now formally state this theorem. The theorem states every composite number can be expressed as a product of primes, and this factorization is unique apart from order in which the prime factors. Actually, it means given any positive number, there is one and only one way to write it as a product of primes, as long as we are not particular about the order in which the prime occurs. So, for example, we regard 2 into 3 into 5 into 7 as same as 3 into 5 into 7 into 2, or any other possible order in which these primes are written. This fact is also stated in the following form. The prime factorization of natural number is unique except for the order of its factors. The fundamental theorem of arithmetic has many applications. Let us look at some examples. So, in the first example, we'll consider the number 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. If the number 4 to the power n for any n were to end with the digit 0, then it would be divisible by 5. That is, the prime factorization of 4 to the power n would contain the prime 5. This is not possible because 4 to the power n is equal to 2 to the power twice n. So the only prime in the factorization of 4 to the power n is 2. Now the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4 to the power n. So there is no natural number n for which 4 to the power n ends with the digit 0. We have learned how to find HCF and LCM of two positive integers using fundamental of the theorem of arithmetic in earlier classes. This method is also called prime factorization. So we have worked out some examples here. Find LCM and HCF of 6 and 20 by the prime factorization method. So you see, 6 equal to, it can write as 2 into 3, and 20 can be written as 2 into 2 into 5, which is ultimately equal to 2 square into 5. Therefore, HCF of 6 and 20 is equal to 2, and LCM of 6 and 20 is 2 into 2 into 3 into 5, which is equal to 60. Note that HCF of 6 and 20 is equal to product of smallest part. So here it is very important, you have to understand this: product of smallest power of each common prime factor in the numbers. HCF of two numbers is product of smallest power of each common prime factor in the numbers, whereas LCM of 6 and 20 is 2 square into 3 into 5, which is equal to product of greatest power of each prime factor involved in the numbers. So we have noticed that HCF of 6 and 20 and LCM of 6 and 20 is equal to 6 into 20. In fact, we can write that for any two positive integer a and b, HCF of ab into LCM of ab is equal to a into b. We can use this result to find LCM of two positive integers if we have already found HCF of two positive integers. So now we'll discuss about irrational numbers. We know irrational numbers is written as a number S is called irrational if it cannot be written in the form of p by q, where p and q are integers and q not equal to 0. Some examples of irrational numbers with which we are already familiar are root 2, root 3, 15, minus root 3 by root 2, pi, 0.10111, etc. To prove that root 2 is irrational, we need the following theorem, whose proof is based on the fundamental theorem of arithmetic. The theorem is stated without proof that p be a prime number if p divide a square, then p divides a, where a is a positive integer. Prove that root 2 is irrational. So here it is proved. See, we have first assumed that root 2 is rational. After that, so root 2 can be written as a by b, where a and b are co-prime. So ultimately we have got, by squaring, twice b square is equal to a square. Therefore 2 divides a square and 2 divides a as well by the theorem. So we can write a equal to twice c for some integer c, which implies a square is equal to 4c square, squaring on both sides. So substituting for a, we get twice b square is equal to 4c square, implies b square is equal to twice c square. Therefore 2 divides b square, and so therefore a and b have at least 2 as common factor, but this contradicts the fact that a and b are co-prime. This contradiction has arisen because of our incorrect assumption that root 2 is irrational. So we conclude that root 2 is irrational. One more example. Show that 5 minus root 3 is irrational. So in the same way, we assume to the contrary that 5 minus root 3 is rational. So 5 minus root 3 can be written as a by b, where a and b are co-prime. So ultimately we got root 3 is equal to 5b minus a by b. Since a and b are integers, we get 5b minus a by b is rational, and so root 3 is rational. But this contradicts the fact that root 3 is irrational. This contradiction has arisen because of our wrong assumption 5 minus root 3 is rational. So we conclude that 5 minus root 3 is irrational.